Okay, so we ended the previous video with this lemma and its application to ordinary differential equations, linear differential equations and their solutions. We did not actually discuss the application very rigorously. We will come back to that later. But now we have this lemma. So let's just see let's recall what this actually means. We have in front of us the statement of the lemma, but briefly it means this without all the writings. We have a homomorphism phi from a group G onto a group G bar with kernel K, and say we choose any element G bar in the second group G bar. Then since phi is onto, this G bar will have at least one inverse image. Now the lemma says that the set of all inverse images of G bar is the coset Kx, where x is some particular inverse image of G bar in phi. That means x is some element in G whose phi image is equal to G bar. Now in this situation we look at a special case. A special case immediately presents itself these are languages from the author, okay. Namely, the situation where K is the trivial group consisting of only the identity element in G, in the domain group. If this happens, then what additional can we say? Clearly, if K is identity, then this coset becomes equal to the singleton set consisting of X. We already know that the coset Kx has X as an element in it. If K is in particular E, then Kx is X. It's a singleton set. So what does this tell us about the map phi? Any element G bar chosen in the second group G has exactly one inverse image, because according to this lemma, this is the set of all inverse images of G bar. So every element in the second group has exactly one inverse image. So that says just the fact that phi is a one-to-one mapping. So let's write these things. In this case, by lemma 274, phi is O. We cannot immediately write phi. Let's first write this thing. Every element of, or every element in, same thing, G bar has exactly one inverse image in G. Under phi, of course, that is understood because phi is the only map in the situation. Hence, phi is one-to-one. Now conversely, let's think about the converse also. Conversely, if phi is a one-to-one mapping of G into G bar not even onto, then the kernel of phi is this. What is this converse? To see that the converse is true, you just recall what the kernel of a homomorphism is. It is the set of those elements in the domain group whose images are equal to the identity element of the second group. E bar is the identity element of G bar. Now we know we have proved that the kernel of any homomorphism is a normal subgroup. Before we started the proof, at the very beginning, we proved that the kernel is non-empty and in fact it has the identity element of the domain group, which means that phi of E is equal to E bar. That is, E is an inverse image of E bar under phi. Now if phi is given to be 1 to 1, then this inverse image has to be unique. So that means in this case K will consist of only E, and that's how we are getting this statement. We are concluding this statement. And what about this not even onto? Note that in this converse part we did not need onto-ness of phi anywhere. That's because we are talking about the inverse images of the identity element in the second group, and regardless of whether phi is onto or not, E bar always has at least one inverse image, that is E. So since we are concerned about the inverse image of E bar, because that's what the kernel is after all. If you look carefully, the kernel of a homomorphism is nothing but the inverse image of the identity element of the second group under the homomorphism. So that's why, because of that, we don't need any onto-ness in the converse part, since we are talking about E bar and its inverse images, which has an inverse image, at least one inverse image. Now here, however, in this lemma, the author has thrown in onto-ness as a hypothesis. Do we really need onto-ness here? Onto-ness is, you can see if you look carefully, onto-ness is not a hypothesis that we absolutely need. It has been assumed here only to make the statement of this lemma look good, expressible in a somewhat neat manner. You can state a result which looks exactly like this lemma, where you don't have to need onto-ness. It will look like this. Say phi is a homomorphism from G into G bar. This phi may or may not be onto with kernel K, and say you have chosen G bar to be any element in G bar. Now you look at the conclusion of the lemma. The conclusion of the lemma says these things, where we need an inverse image of G bar, which here we have written as X. Onto-ness tells us that at least one X exists. If we don't have onto-ness like what we have here, not necessarily we don't necessarily have onto-ness, then you have to additionally mention that G bar is not any element in G bar, but rather an element in G bar which has at least one inverse image. To avoid writing all those things, it looks somewhat awkward. The author has decided to throw onto-ness as a hypothesis inside this lemma and state it neatly. We need only onto-ness only for that purpose. It's not fundamental to the lemma. Okay, so now we have this situation where the one-to-oneness of a homomorphism has been linked to the kernel of the homomorphism. Now next we have a definition that is about homomorphisms that are one-to-one, because one-to-one homomorphisms have appeared in this way. They can be considered independently, but they have appeared in this way, linked to the kernel. So here is the definition. And it just is this: a homomorphism phi from a group G to a group G bar, that is one-to-one, is called an isomorphism. So according to this analysis, isomorphisms are, by definition of course, isomorphisms are one-to-one homomorphisms. That's what they are. But according to this analysis, isomorphisms are precisely those homomorphisms whose kernels are all the trivial group. Unfortunately, this term isomorphism does not have this single meaning throughout mathematics. Some people require an isomorphism to also be onto. That means for them an isomorphism is a bijective homomorphism as opposed to just an injective homomorphism here. Herstein has decided to use the term isomorphism for injective or one-to-one homomorphisms. Some other people may use it for bijective homomorphism. It's somewhat unfortunate that it's not just this case, but there are many such things in mathematics where a single term is used in different ways, that is, it has different meaning to different authors. But what can we do? We have famous mathematicians, and once they use something, another famous mathematician in the same field uses that same term in a somewhat different way. Both of them are followed. Some people prefer one, some people prefer the other. Next, there is another definition. Two groups G and G star are said to be isomorphic. Isomorphic, or we also express this by saying that G is isomorphic to G star if there is an isomorphism of G onto G star. That means G and G star are said to be isomorphic if there is an isomorphism of G onto G star, or in other words, there is a bijective homomorphism of G onto G star whose domain is G and whose codomain or range, whatever you may call that, is G star. That is, the second set is G star. Oh, I have to mention that also. When G and G star are isomorphic, let me write in brackets, we also say that G is isomorphic to are isomorphic, then we express that statement by writing this. It means G is isomorphic to G star, that there is an onto isomorphism from G to G star. Now, a fundamental fact about isomorphisms is that the relation of two groups being isomorphic is like an equivalence relation. It is reflexive, symmetric and transitive in the class of all groups. I am saying like equivalence relations because primarily so far I know equivalence relations are defined on sets. However, when we take the set of all groups, we generally don't say set of all groups, we say class of all groups. Whether that forms a set or not, that is a different matter altogether. To be on the safe side, we say this relation is like an equivalence relation. What matters is what that means. The name does not matter really. For any three groups G, G star and G double star, we have these things, these facts. G is isomorphic to itself. Number 2. If G is isomorphic to G star, then G star is also isomorphic to G. And number 3, if G is isomorphic to G star and G star is isomorphic to G double star, then G is isomorphic to G double star. Okay, let's see why these things are true. Consider the identity map or identity mapping F from G to G. By definition, this is given by this formula. Every element is mapped onto itself. We know that F is 1-to-1 and onto. This we already know. The identity map on any set is 1-to-1 and onto. And also that F is a homomorphism. In the very first example of homomorphisms between two groups, we have seen that the identity map is a homomorphism. So that's it. F is an isomorphism of G onto itself. Hence, G is isomorphic to itself. Next, let G be isomorphic to G star. Then let me put some ink first. Then there is an onto isomorphism from G to G star. Phi from G to G star. Since phi is bijective, it's onto, and since it's an isomorphism, it's one-to-one also. So that means it's bijective. Its inverse, phi inverse from G star to G exists. Okay, as a mapping, the inverse exists. Now we aim to prove that this phi inverse itself is also a homomorphism. We already know that the inverse of a bijective map is itself bijective. So if we can show that this is a homomorphism, then this will be an isomorphism from G star onto G, proving that G star is isomorphic to G. That's what we want to now do. So to show that it's a homomorphism, we consider two elements here. Let G1 and G2 be two elements in G star. Then there exist unique elements H1 and H2 in G, such that phi of H1 is equal to G1 and phi of H2 is equal to G2. For G1, H1 exists because phi is onto, and H1 is unique because phi is one-to-one. That's how we have the existence and uniqueness of H1. But then, by the very definition of this inverse function, phi inverse of G1 is equal to H1 and phi inverse of G2 is equal to H2. Now what happens when we calculate this? Phi inverse of G1, G2. Note that G1 is phi of H1, so let's use that here. Like that, G2 is phi of H2. Inverse is there outside, let's just keep it like that. Now inside, because phi itself is a homomorphism, so phi of H1, H2 will be phi of H1, phi of H2 will be phi of H1, H2. Now you use the fact that we have phi inverse and phi. So this is equal to H1, H2. But H1 is phi inverse of G1 and H2 is phi inverse of G2. So phi inverse of G1, G2 is phi inverse of G1, phi inverse of G2. This shows that power is gone. Anyway, this shows that phi inverse is a homomorphism. Since we know that phi inverse is bijective, phi inverse is thus an isomorphism of G star onto G. So G star is isomorphic to G. Okay, so we have proved that this relation is symmetrical on the class of all groups. Next, let G be isomorphic to G star and G star be isomorphic to G double star. Then there exist onto isomorphisms. So let's name them phi 1 from G to G star and phi 2 from G star to G double star. We know, here I have to be careful in forming the of course you can almost guess what we are going to do. We will take the composition of phi 1 and phi 2. That will give us a mapping from G to G double star. But in writing that map, I have to be careful about whether I should write phi 1 composition phi 2 or phi 2 composition phi 1. That will depend on which side of the function I am writing the argument. Here I have been writing the argument normally like how we write arguments in mathematics, not to the left of the function but to the right of the function. So here I have to change the order. Phi 2 composition phi 1, that will be our mapping from G to G double star. Why? Because since I am writing arguments to the right of the map, so there I will be able to first apply phi 1 and then on that result I can apply phi 2. If I write arguments to the left, then I don't have to change the order. Okay, so what do we know about this? Since this is an isomorphism, each one of them is an isomorphism, that is onto, in particular each mapping here is a bijection. So that's why this composition is also a bijection. We know this is a bijection since phi 1 and phi 2 are bijections. So we now have, the only thing we are left to show now is that this composition is, apart from being a bijection, it's a homomorphism. So let us take alpha and beta to be two elements in G. Then using the fact that phi 1 and phi 2 are homomorphisms, we have phi 2 composition phi 1 alpha beta. By the definition of composition, this is phi 2 of phi 1 of alpha beta, and that is equal to because phi 1 is a homomorphism, we can write this as phi 1 alpha, phi 1 beta. But because phi 1 maps G into G star, so phi 1 alpha and phi 1 beta are both elements in G star, and phi 2 is a homomorphism from G star to G double star. So this will be equal to phi 2 of phi 1 of alpha times phi 2 of phi 1 of beta, and again you apply the definition of composition of two functions. This is phi 2 composition phi 1 alpha times phi 2 composition phi 1 beta. So this is a homomorphism. And bijectivity of this map now tells us that it's an isomorphism of G onto G double star. Composition phi 1 is an isomorphism of G onto G double star. This shows G is isomorphic to G double star. So we have proved these three properties of the relationship of two groups being isomorphic, like an equivalence relation. Now, what does this mean? What does it mean for two groups to be isomorphic? In a sense, when two groups are isomorphic, they are algebraically exactly the same thing, only their elements have been named differently. In that regard, there are some things the author says. When two groups are isomorphic, then in some sense they are actually equal. They can be considered as one thing rather than being two things. The two different looking groups which are isomorphic are just two different representations of the same underlying group. It's like calling a person by two names. The person, underlying person does not change, only the names, that is the representation of the person, there are more than one, that they are equal. They only differ in that their elements are labeled differently. The isomorphism gives us a key to this labeling. What else is the author saying? And with it, knowing a given computation, yes, in one group we can carry out a similar computation in the other group. We have already discussed about this when we defined homomorphisms themselves, that how a homomorphism between two groups is actually like a mirror, where on one side you have the actual object, on the other side you have its mirror image. Whatever calculation is happening here, say we are taking two elements A and B to calculate the product AB in the group. An exact similar calculation is available in the mirror world. Where in place of A you have its mirror image phi of A. In place of B you have its mirror image phi of B. Just like this one, you can calculate the product phi A, phi B. Homomorphism says that if instead of calculating the product here, you calculate the product here and then then you look at the mirror image of this product, then these two things are equal. Isomorphism makes this even more equal in the sense that in a homomorphism, okay, some elements may be missed by the homomorphism. If the homomorphism is not onto, then some elements may lie outside of its range or outside of the image set consisting of all the outputs of the function. Then that will not partake in any calculation. Just like that, if the function phi is not one-to-one, then there are collapses, right? Some elements are mapped onto the same element. So an element having or rather a mirror image coming from a same object, that is no longer true. Two different elements may have the same mirror image, but in an isomorphism which is onto, there is a one-to-one correspondence between an object and its mirror image, just like what we have in the physical world of objects and mirror images. So in this case, whatever is happening in the first group, an exact same thing is happening in the second group. It does not matter what you call these elements, what names you give to these elements. In the first group, we have decided to give them the names A and B. You compose them to form AB. In another world, you call them phi of A and phi of B. You compose them to form the element phi A, phi B. It turns out that they are exactly the same calculation in this sense. Okay, it's like adding, say, in the additive group of integers. If I add 1 and 2, I have 3. Okay, in this group. In another language, in my mother tongue, say Bengali, we use different symbols for the same numbers. Strictly speaking, I will get a different additive group of integers, where in place of 1 we write a symbol like this. In place of 2 we write a symbol like this. And in place of 3 we have a symbol like this. Truly, you can see that underlying these two calculations, there is a single thing going on. Only the representations are different. So the same thing happens when we do calculations in isomorphic groups. Whether you consider them, there is no point in considering them to be different groups actually. Algebraically or group theoretically, they are the same thing, just like this one. Okay, that's why the author says in some sense they are equal. They only differ in that their elements are labeled or named differently. And then there is another analogy also. The isomorphism is like a dictionary which translates, I mean, you know what a dictionary does, which enables one to translate a sentence in one language into a sentence with the same meaning in another language. A given sentence in one language to a sentence with the same meaning in another language. The isomorphism enables one to translate a sentence in English into a sentence in Bengali having the same meaning. Of course, these are mathematical sentences having the same meaning, that underlying meaning is the same. But merely to say that two groups, or I think he is saying about a given, yes, a sentence can be expressed, or a sentence in one language. I am writing all these things because I don't want to really miss anything minute or subtle that the author has said or intended to say in these sentences, but merely to say that a sentence in one language can be translated in another language may be of little importance. One needs the dictionary to carry out the translation. The dictionary itself is more important than the mere fact that, say, you have one sentence in English and you say that it can be translated into a sentence with the same meaning in another language. That statement by itself may not be of much importance, but the fact that there is a dictionary and it can be used to carry out that translation, that dictionary may itself be more important. Just like that, similarly, merely saying that two groups are isomorphic may be of little consequence. The object of interest may very well be the isomorphism itself. And that is why when we try to show that two groups are isomorphic to each other, we will try to provide the isomorphism also. Okay, we won't in most of, as far as possible, we won't show that two groups are isomorphic by some indirect method. Of course we will do that, but we will always try to present one actual map between two groups that provides us with such an isomorphism. Okay, so now returning to that lemma 274 and its special case, from where we have seen that there is a way of characterizing one-to-one isomorphisms, we state a corollary to that lemma 274. Whose proof we have actually seen already after the statement of 274 was given. I mean, that analysis we did where we saw that a homomorphism is one-to-one if and only if its kernel is identity. That's what we are going to just state here. A homomorphism phi from a group G to a group G bar with kernel K phi is an, now we can say isomorphism, we have that language. If and only if K phi equals the identity element. Okay. Now, this corollary provides us with a standard technique of showing that a homomorphism is actually an isomorphism. So first you show that a given function is a homomorphism, and then you look at its kernel, and you then have the fact that it is an isomorphism if and only if the kernel consists of only the identity element. So if you want to show that a homomorphism is an isomorphism, look at its kernel, show that it's equal to E, then that proves that it's an isomorphism. Okay, now this corollary also gives us something else. Say you have two groups, G and G star, say I am considering G star, and you have been able to prove that there is a homomorphism phi from G onto G star, and then you show that the kernel of phi is the trivial group, then phi becomes one-to-one also. So that means phi becomes an isomorphism of G onto G star, that is G is isomorphic to G star. This particular strategy of showing that two groups are isomorphic to each other will be used again and again, and immediately it will be used in showing this next very important theorem, which says that under some circumstances we can, let me just state the theorem, then we can understand what it means. Its proof we will do in the next video along with other things, but at least let us just see the statement. Let phi be a homomorphism of a group G onto a group G bar with kernel K. Then G bar is isomorphic to the quotient group G by K. Okay, this is a very important result. It's let us first see what it says. It says that there is a homomorphism phi of G onto G bar, just like this situation, and the kernel of phi is given to be K. Then if you form, we already know that K being the kernel of a homomorphism is a normal subgroup of G. So that means we can form the quotient group G by K. It turns out that these two groups are isomorphic. Okay, so that is the meaning. But what is the consequence of this? Why is this theorem so important? It's important for one reason. Note that G bar is a homomorphic image of G. That is, it is the image of some homomorphism applied on G. That is, it is equal to phi of G. And image, because it's onto, we will get entire G bar from G and phi. So if a group is given to us, say we are applying different homomorphisms to it, phi 1, phi 2, phi 3, etc., and we are getting different homomorphic images, phi 1 of G, phi 2 of G, phi 3 of G. These are all groups which are homomorphic images of G. This theorem says that instead of considering these homomorphic images, or in other words, instead of leaving the group G, you can be inside G and get all the homomorphic images. All you have to do is you consider the normal subgroups of G and form the quotient groups. According to a previous lemma, these quotient groups themselves are homomorphic images, because we have seen that, okay, let me just say some more things. We have already seen that if we consider this function from, say, G to G by n1, where n1 is some normal subgroup of G, where the element G is mapped onto the coset n1G, then this mapping is a itself a homomorphism and onto. So that means G by N1 is a homomorphic image. That just says that if we keep on forming quotients of a group by its normal subgroups, we are getting homomorphic images of the given group. This theorem additionally says that these are the only homomorphic images. We won't get anything new, any homomorphic image that cannot be obtained in this by this scheme. Okay, in this way we will actually obtain all the homomorphic images, because if we have one homomorphic image, then it is the same as a quotient like this, and this entire thing tells us that there is a one-to-one correspondence between homomorphic images and normal subgroups of a group. If you want to get the homomorphic images, you just look at the normal subgroups a group has, form the quotients, you get all the homomorphic images. Okay, so in the next video we will explore this, and of course we have to prove this theorem, and then we will see other things also. So with this I end this video. If you have any doubt regarding these things, you can always write in the comment section, or you can personally mail me also at this address. Let me again write it. So with this I sign off for today. This is me, Lucifer, from a mathematical room. Have a nice night.